Hey there YouTube, it's your boy Lipid out here with another Veritasium video. Today we got what happens if you throw sand into a jet engine. Let's get right into it, shall we? Hit it.
This is one of the most powerful jet engines in the world, and it actually runs at temperatures 250 degrees Celsius hotter than the melting point of the materials that make it up.
That's 1200 degrees.
So the question is, why doesn't a jet engine just melt into a puddle?
Airflow. This is my best guess, probably.
The boundaries of the laws of physics.
That is wild. It's at the same temperature now as it would be inside the jet engine.
Ooh.
But here they're liquid.
Every time I get on a plane, I'm thinking, this is never going to work.
And yet, it does work. Right now, there are over 10,000 planes.
The terrifying thing is it's still the most reliable form of transportation, even with all the things that have been happening recently, which is
in the sky, powered by engines just like these.
It's crazy to think that just those two power plants like make the world move, which is just incredible.
Maybe you are on one right now. So how do they work?
Turbofan.
This is a jet engine, specifically a turbofan engine.
Also, yeah, just fair point about myself. I am a huge aviation geek. This is, it just feels nice just coming back into something that I just enjoy watching. And that to Veritasium covering it is just nice.
At the front is this giant fan.
The cone.
During takeoff, these rotating blades push 1.3 tons of air backwards every second. And around 10% of that air gets compressed.
These are also called bypass engines because a large part of that air just doesn't even make it through the compression chamber, just makes it all the way around it.
Compressors force the air into increasingly narrow chambers. They compress the air to about 50 times atmospheric pressure.
Inject fuel.
Just by doing that, the air heats up to around 600 degrees Celsius. This compressed air is then forced into the combustion chamber, where fuel is sprayed in through a ring of nozzles and ignited. That chemical reaction gives off a lot of heat, so the temperature jumps to around 1500 degrees Celsius.
And what's crazy is it is these, from what I understand, it is these rotating discs that are also feeding back this rotational energy for the front part. It's basically back powering the front, isn't it?
So now you've got this high pressure gas from the combustor that just wants to expand. And now it's got an incredible amount of thermal energy. But between the combustion chamber and the outside air is this. Rows of turbine blades. So in order for the gas to expand and get out, it needs to push these turbine blades out of the way. And in pushing the blades, that is how it transfers its energy to the engine. This is where all the power really comes from. In modern jets, on takeoff, each high-pressure turbine blade is generating as much power as a Formula One car. And there are
I'm sorry if I heard him right. He means every blade?
High-pressure turbine blade is generating as much power as a Formula One car.
So that's just visualizing that is insane.
And there are 68 of them. As the gas rushes through the turbine and nozzle, its pressure drops from around 50 atmospheres down to 1.
Normalizing,
and it expands by almost 20 times. And that spins these turbine blades up to 12,500 revolutions per minute. The fan that is pushing all that air backward and all those compressors that squeeze the air down, all of that is powered by the turbines back here. It's a kind of funny, really counterintuitive way to think about an engine. It's what's happening in the back that's actually driving everything up front. As the hot exhaust gas is shot out the back of the engine, it pushes the engine forward. That generates thrust. But did you know that in a modern passenger jet, this accounts for less than 20% the thrust of the engine?
Right, because I don't know the exact physics or like the exact science behind it, but apparently higher bypass ratios give you much more thrust. So high bypass ratio engines are just not only more fuel efficient, they're quieter, they effectively they work longer and they work better and they're more reliable.
The vast majority of the thrust, over 80% of it, just comes from that big fan at the front of the jet.
Pushing air back.
Remember how only 10% of the incoming air gets compressed? The other
General Electric,
90% bypasses all that. It's simple.
And if I'm not wrong, I think it's General Electric and Rolls-Royce that makes most of the engines. I think Pratt & Whitney does as well, if I'm not wrong.
Simply propelled backwards by the fan. It goes right around the guts of the engine and comes straight out the back. The fan pushes that air backwards, so the air pushes the fan forwards. That's how you get 80% of the thrust. It's basically a huge ducted propeller. So why do it this way? I mean, why not compress all the incoming air and put it all through the combustion chamber and turbines?
Less efficient, probably?
Well, some fighter jets do exactly this, and it makes for very powerful engines, but they're also horribly inefficient. To see why, remember that the impulse pushing the plane forward is equal to the change in the momentum of the air backwards. So you've got options. For example, you could push twice as much air back half as fast.
For the same
or
momentum.
you could push half as much air back
Twice as
as
fast.
fast. Both will generate the exact same impulse, but the kinetic energy of the air is proportional to v squared. So it takes 4 times as much energy to speed up the air in the second case, and a lot of that energy is just wasted in the exhaust.
Oh.
So ideally, you want to push as much air backwards as possible with only a small change in velocity.
Oh, okay.
That's why jets have gotten bigger and bigger over the years. And the increasing fraction of bypass air has the added benefit that it surrounds the hot exhaust gases, and that
I never understood the math until now, and I'm like, that. The more I'm looking at it, like, that is an awfully simple equation to explain why engines are getting fatter. It's like, huh, that's interesting. That is interesting, huh?
reduces noise.
Yeah, it does make sense. You would much rather have more of the air flowing out instead of making it go faster. Yeah, fair enough.
Coming away from the
4
jet.
times the kinetic energy.
But
for it,
there
right?
is
Yeah, fair
another
enough.
major factor when it comes to engine efficiency, and that is temperature. At cruising altitudes around 35,000 feet,
We're talking like what, -20, -30?
the outside air is around -55 degrees Celsius.
Look, I did not know that, but damn.
Well,
Okay.
inside the engine, it's over 1,500 degrees Celsius. The hot, high-pressure gas inside the engine wants to expand into the much colder, lower-pressure air outside. It's that difference that lets the engine turn heat into useful work.
That actually makes sense. I always wondered why, but okay, that makes sense why engines are more efficient at higher altitudes, isn't it? Okay, that's interesting.
But there's a fundamental limit to how much...
I mean, counterintuitively, I always imagined that the higher up you went and the thinner the atmosphere got, it was harder for the engines to push as much air through the engine. So I always did wonder it. Okay, huh.
work any heat engine can get from that. It's called
The
the Carnot
Carnot,
efficiency. It's equal to 1 minus the temperature of the cold outside air divided by the temperature of the hot gas
I remember college teaching me this, chat.
inside the combustion chamber.
I remember it.
So, looking at this, you can improve the efficiency of the engine in 2 ways. Either fly where the air is colder, or raise the temperature in the combustion chamber.
Which is also interesting because I imagine this is exactly the reason why, especially if you're in the Middle East and it gets... Summers are brutal here. We're talking like plus 50 degrees Celsius, like even hotter, 52, 54. With including humidity, you might be pushing 60. Like healthcare and health risk aside, you standing outside for even a few minutes could be life-threatening. But it's always one of those things where I imagine like where certain companies also did mention that under extremely hot and humid conditions, your engine performance is degraded. Not enough that it doesn't work, but it is degraded enough that you have to consider that in your flight calculations to set the appropriate thrust settings to take off. So yeah, it's
One
known.
problem with that, though, is
And not to mention hot air produces less lift.
it turned the inside of a jet engine into one of the harshest environments we have ever built, in which machinery has to survive.
To keep a turbine
That too reliably. Remember, there have been entire accidents in the past where you have material defects that have caused that core component of those fan blades to separate. You have to understand, those things are under immense stresses. Like, it's unimaginable. Like, you're rotating 10,000 plus rotations per minute. Under those temperatures, the amount of flexing and any imperfection in that material it may not be immediate, but you're talking, it could be randomly at some point in time. And a failure at something that's moving that fast will rip shrapnel. Like, your engine cowling that's protecting the engine can only do so much. When something going that fast, that hard, that hot just separates, it's destructive. There have been accidents in the past where the failure of just one of those damages hydraulic lines, reduces the capability of the pilots to control the plane, and has caused accidents before.
turbine blade whole and unaffected within an engine
Yeah.
is like putting an ice cube inside your oven, turning up to max, leaving for work, coming back after an 8-hour shift and finding it still completely frozen in the oven. That's what
The only time that's a very nice analogy, but the only time I've seen something like that ever done, there's a clip from the NASA materials research lab from I think 5 to 10 years ago, and they had a kiln, it's KIL, and it's a kiln where they have this heated oven. They put materials into it, And I think, I don't know if I'll find the video. They put the materials outside. They took some of the materials outside. They're like cubes that if you take, it's hot and they're like thousands of degrees Celsius. They put it outside and then people with their hands were able to pick it up on the edges because it was already immediately cooling off. And it's apparently part of the reflective shielding that's on the base plate of like the space shuttle. And I'm like, that's fascinating. The moment I saw that, I was like, bro, that's black magic. I don't know what type of materials science you had to go through to develop something like that, because that looks illegal. Like that looks physics would probably look at that and say, what you doing? What you doing over there? That's crazy.
That's what we've got to try and do within that engine.
Yeah.
That sounds absurd.
Yeah. Not to mention reliably, any defect on any one of these, or even for a small batch, will lead to like entire planes being grounded. This is just mind-boggling, to say the least, right? Jeez.
Not only do the turbine blades sit in a stream of gas that's over 1,500 degrees
Yeah.
Celsius, they're also spinning at 12,500 RPM,
Yeah.
with the tip of each blade slicing through the air at nearly 1,900 kilometers per hour.
Mm-hmm.
Now, every blade wants to fly straight, but it's forced to spin in a circle,
Yeah.
which means something has to be constantly pulling it inwards. That's the
Centripetal
centripetal force.
force, okay.
If you take a representative 300-gram high-pressure turbine blade and run it at that speed and radius, it has to be pulled inwards with a force equal to the weight of 20 metric tons. That's roughly the weight of 2 London double-decker buses tugging on each blade as it spins, all while they're glowing hot.
Yep. It is. And I know in the nicest way possible, showing this kind of tech to someone just from 100 years ago, they'd probably stab you for being a witch. If you showed this to someone from 50 years ago, when after flying was invented and all that, they'll still shoot you, which is just it's crazy.
To make matters worse, at these temperatures, oxygen wants to react with the metal of the blades itself.
Ooh.
And on top of all that, the air rushing through the engine often carries dust, sand, and pollutants that
Hold on.
can damage and erode the surfaces inside.
And it's one of those things where, because if you've watched Air Crash Investigation, there have been entire episodes dedicated to this. One of them in particular was, there's a volcanic eruption on the island of Java in Sumatra. I think it's next to Indonesia only. And it's just, I forgot what the plane was. I think it was a British Airways flight. And you have 4 engines dying because you have all this volcanic ash, clouds of dust that enter the engines, melt, but then stick within like the walls of like not only the rotary blades and the fan blades inside, and and starve the engine of oxygen, shutting it down. And I'm like, bro, imagine just in flight and 4 engines just slowly shut down. At the same time, you have St. Elmo's fire, which is like the electrostatic kind of discharge. It's like a lot of like high energy particles like hitting rubbing against like the windshield, and it just looks like an illuminating light. There's so many cool phenomena here. Like you could talk for hours about it, but dust and particles like this, especially volcanic ash, can shut down engines. It's happened before, yes.
And somehow these blades
if you spoiler alert, I don't know if you do disaster results count as spoiler alerts, chat? Do they really? Regardless, the reason why that British Airways flight managed to make it out, if I'm not wrong, from the investigation, was because given enough cooling time, those buildup of volcanic ash within the engines cooled off, broke up, departed the engine, allowing the engines to be restarted. And hence they were able to land, which is still luck of the draw. You feel me? That is just insane.
to survive this punishment for tens of thousands of flight hours without deforming, cracking, or failing.
Yep.
They really determine how efficient you can make the engine,
Right.
because you can't make the engine so hot that the blades can't withstand that temperature.
So
They determine the maximum temperature of the combustion chamber and therefore the maximum efficiency you can realize with a jet engine. So what kind of metal could possibly survive these conditions?
My first guess would have been titanium, but I'm guessing they've probably advanced well beyond that.
we sent Veritasium producer Amelia to the Department of
Steel would
Materials
give up.
Science and
Steel would
Metallurgy
not
at
survive
Cambridge
them.
University to put some different metals to the test.
So this is the steel.
This is the steel
Yeah,
sample.
that's not-
Yes.
Okay.
So go back to
Even properly impregnated steel, like properly impinged with like other like metals, wouldn't survive. No, I
200
don't.
megapascals
I don't
to
think
start
so.
with, which is sort of comparable to
some of the stress that's seen by these components in real applications.
Sure, but those temperatures, no.
And we're going to put that stress on and then slowly increase the temperature.
This is a mild steel. It's relatively strong and easy to form into complex shapes. It seems like a pretty good bet for a turbine blade, and at first, under this load and at these low temperatures, it holds up pretty well. We're essentially tugging on all the atoms within the metal. We're not breaking or forming any bonds. We're just making them flex a little, and that slightly changes the spacing between the atoms, and as a result, the metal gets slightly longer. This resulting change in size, specifically the per unit change in length, is what we call strain. Critically, at this stage, the material is behaving elastically. If we remove the load right now, the material just snaps back to its original size.
Right. And a plastic deformation is well beyond that, and it just, inelastic deformation, which means you're going to have a deformation that's permanent, and that's going to be a permanent damage to the structure. It's not going to be as strong, right? Yeah.
In an engine, some elastic deformation like this will occur.
Yeah.
It can't be too big or it'll cause problems. But what we really don't want is plastic deformation if the shape changes permanently. And that's exactly what starts to happen as we keep increasing the temperature.
Yeah.
It's getting hot now.
Yeah.
That's a little bit of oxide. There you go. See this starting to deform.
Rapid deformation,
now,
and then failure.
Bonds are breaking and reforming as the metal lattice deforms permanently.
And reaches failure, fail.
But this doesn't happen all at once. So I got the mechanical engineer on our team, Henry, to build this demo.
Okay, so you can see we're getting a bunch of tiny little bubbles, and just naturally they're packing into this hexagonal arrangement. And there are actually a lot of materials that have atomic structures just like this. But you can see it's not perfect.
Right.
Like right here, you can see there's an extra half plane of atoms. Well, in this case, bubbles. This is called an edge dislocation.
And it's spreading. It moves.
And it becomes really interesting when I try to pull this raft apart. You can see these little dark lines that zip back and forth.
Yeah.
Those are dislocations, and they move through the lattice. As the dislocation moves, it'll cause one plane of bubbles to shear past the other one, which shifts the structure by exactly one spacing. But there isn't just one dislocation.
Yeah, it's multiple.
There are plenty of them. And altogether, their movement produces dramatic changes in the overall shape.
Yeah.
That's exactly what's happening here. Everywhere that stress is high enough, billions of dislocations are moving and interacting. The steel starts to deform continuously under this constant load in a process called creep. It takes energy to break the atomic bonds as a dislocation travels through the lattice, so as we ramp up the temperature and all the atoms get more thermal energy, it no longer requires as much stress to break these bonds. It becomes much easier for the dislocations to move. The metal effectively gets softer. Now the steel's strength drops so much that the slow, time-dependent creep gives way to rapid deformation. As it stretches, it rapidly decreases in cross-section, and eventually the remaining metal can no longer bear the load.
Crazy,
now you
isn't
could
it?
try doing similar tests for other metals, like this titanium alloy.
Maybe better?
Titanium is about half as dense
he said
as
alloy as well, so fair enough.
steel.
Should feel that's quite a bit lighter.
Yeah, it's like loads lighter.
So if we were to make
This
turbine
is literally the iPhone stainless steel versus the iPhone titanium argument. One is lighter, but I don't think...
blades out of titanium, each blade would be
Tensile strength is roughly similar, if I'm not wrong, isn't
much
it?
lighter, and that would reduce the enormous centripetal forces it would experience. So it seems like a great choice. And at first, it performs really well.
That's 100 degrees. It's hanging in there.
But as we push the temperature higher,
Oh, I can see some
It still
glowing.
fails.
Oh, look at this. Oh, it's gone already.
Fail. Yeah. Oh, rough.
just
Even
like the
less
steel,
temperature.
its strength drops rapidly as temperature increases. And that's true for most metals. Yet the first jet engine dating back all the way to 1941 actually did use steel turbine blades.
Oh.
It was designed by British pilot and engineer Frank Whittle. His engine powered the first flight of a British jet aircraft, the Gloucester E-2839 prototype. When a colleague excitedly told Whittle, "Frank, it flies," he dryly quipped, "That was bloody well what it was designed to do, wasn't it?"
British humor at its finest, nice.
But Whittle's prototype had two major flaws. The first was that the gas inside the engine only reached temperatures of around 780 degrees Celsius.
Which, to be fair, for its time, I'm guessing, revolutionary.
Which was one of the reasons it was inefficient. And the second was that it was only allowed to fly for up to 10 hours. any longer, and it was too likely parts inside the engine would
Will fail, okay.
And both of these drawbacks were largely due to the steel turbine blades.
Oh, okay.
Something that occurred to me is, why aren't they made out of tungsten? I mean, because tungsten doesn't melt until 3,400 degrees Celsius, which is more than twice the temperature inside a modern jet engine.
Think could be weight restriction, density?
But tungsten is also incredibly dense. It's about 2.5 times denser than steel, and it's also brittle, which makes it hard to manufacture. And using a material that heavy wouldn't just make the blade a problem, the components that hold the blade in the engine would also have to carry much higher loads, well beyond what current materials can handle.
So you'd be tweaking with a lot more than just,
you can optimize for one thing like the melting point, or a different thing like strength or weight, but the turbine pushes every variable to its limit. So what are these blades actually made of? Well, to find out, we went to Rolls-Royce's precision casting facility in Derby. And it turns out the world's most advanced metal parts begin life as, well, something surprising.
What is with the pink and the green there?
I'll come and show you.
I'm just seeing so many cool things around here. I'm like, what is that? Why does it look like that? You just enter this room and I smell the wax.
Yeah.
It smells like a candle factory in here.
Absolutely. So investment casting is a really, really ancient technology. So our ancestors have been doing investment casting to make jewelry, to make weapons for millennia. We've just perfected it here to make turbine blades.
It's so wacky. This is just not how I'd expect it to happen at all. Turbine blades strike me as one of the most high-tech things in the world.
Yep.
And yet, this facility is using wax as a starting point.
What you will see through our tour today is that actually it's a really highly technological process. This is our wax pattern die. This is how a turbine blade starts.
I'm still guessing the wax is obviously to form like a mold that you're going to then pour something into. You're not probably going to use wax itself, probably, right?
Starts its life. So this is what's going to go inside the wax pattern.
Okay.
A ceramic core. This is going to create a hollow inside the turbine blade. So what's happening now is we're injecting into the die. So that's the very start of the life of a turbine blade.
That is really neat.
Interesting.
What we'll actually see is that a lot of these features, such as the aerofoil and the annular surfaces, are not touched further. So we will cast that, and that will remain as cast as it goes into the engine.
Oh.
Every surface here has to be perfect because this wax is what will become the blade.
So Kim is our wax pattern assembler. So she's responsible for taking the product straight from that die, making sure that things like die lines have been removed, so where the die blocks come together and leave a small amount of flash. The operative word in all of wax assembly is smooth.
There is no way this is handmade. Bro, this has to be automated. Really, come on.
Every tiny imperfection in the wax would become a
There's no way.
flaw in the metal. So this takes an incredible amount of skill.
Then it's the case of getting that wax pattern attached to the unit runner to create the assembly.
I mean, the thought that occurs to me, right? Shouldn't you be doing this with a robot?
Yeah, I would presume that for that level of accuracy, you want from, I don't know, millions of blades, maybe?
Yeah. So Rolls-Royce has facilities that do this by robot, but our facility in particular is very much focused on bringing in those new products. And it's far easier for us to work with human beings to develop that method.
So I think maybe like putting in bleeding edge just to figure out, okay, maybe if there's a different way of doing it better.
The manufacturer that's going to bring the next generation of product through.
I'll bet. I can see the skill here. Like, it's phenomenal.
Yeah,
I'll just make a mess of it.
Absolutely, so would I.
Would you like it?
No. Once the wax assembly is perfect,
What am I looking at? Holy. What is... So yeah, that's the blade. What is this? It's a base plate? What? Okay. What the?
It's ready for the next stage.
Everything that is wax is going to become air. It's going to become negative space, right? It's going to become our cavity. And then we're going to fill that air with metal.
This is fascinating, by the way.
So we take that wax assembly and we've got to build a shell.
There's the robots I'm used to. Okay.
Shell is made of many different layers. It's a zircon-based shell system. We're going to dip into a primary slurry. It's really quite thin, like a light syrup or a thin honey.
Oh, yeah.
And what that's designed to do is map all of those really complex geometric features.
Beautiful. It's like making icing.
Huh.
So that's actually the analogy we use. So it's a bit like if you put icing on top of a bun or a cake, you need to sprinkle it with some sugar afterwards, otherwise it's all going to slop off the top. So we've got the slurry on there, we're going to get a nice even coat, drain it, make sure that it's an even thin layer, and then we're going to sand, and that's then going to set that layer in place.
So cool.
Whoa. We're then going to dry it, so it's air dried for many, many hours, and then we can create our backup layers. So our backup layers, it's a much thicker slurry, more like a treacle, and the sand is much coarser, more like a granulated sugar. And we're going to maybe put 4, 5, maybe even 6 layers to back up, because what we need is a mold that can withstand the casting parameters that we're putting it under. You know, it's got a lot of work to do.
Harsh, yeah.
The wax is then melted out.
Okay, so that makes sense. Okay, so you have the wax that forms the base, and then you put all these other layers on it, coating it, and then you melt the wax out.
And the mold is fired.
Okay.
That is wild.
That makes
Cleaned and
sense.
tested to make sure there aren't any cracks.
Interesting.
When it's done, the shell is ready to hold molten metal.
This is a billet of alloy that's going to fill the whole of that mold. So just that amount of metal is going to fill that whole mold there.
It doesn't look like enough.
This is a nickel alloy. The first nickel alloys used in jet engines were developed in the 1940s. By adding chromium and cobalt, engineers created alloys that could handle 800 to 900 degrees Celsius, around 100 degrees hotter than the steel used before. And these alloys could keep their strength for thousands of hours, a 10-fold improvement in life. But the real breakthrough came when they added a touch of aluminum. So we wanted to see how it held up under the same lab conditions as the steel and titanium.
Nickel
What temperature are
super
we at now?
alloy.
Oh, that's
700.
degrees.
Wow.
700. So steel's longer.
Yeah.
Steel's long gone.
Yeah.
That's 800 degrees.
800, yes.
Isn't it moving?
In fact, around this temperature, it's actually getting stronger. So why would heating a metal make it stronger? Well, when these nickel alloys were first used in jet engines, no one actually knew. But about 10 years later, electron microscopes had improved enough for engineers to finally see what was happening inside.
That's fascinating that they did something. They just randomly throw in something together and then just say, you know, it works. We still don't know why. Then you have the observation.
As we zoom in on the alloy, a pattern emerges. The microstructure isn't uniform. Instead, it kind of looks like a city grid, made up of blocks with roads in between them. Only each block is so small, over 300 would line up across the width of a human hair. Now, surprisingly, both the roads and the blocks are made up of the exact same atoms, mostly nickel with a little aluminum. They even have the same crystal structure, a grid of tiny cubes with atoms sitting at the corners and at the center of each face. The only difference is that the atoms are arranged slightly differently. In the road structure, the aluminum and nickel can take any spot. There is no repeating sequence from cube to cube, and this is known as the gamma phase. But in the blocks, aluminum always takes the corner spots, and nickel the faces.
So like a fixed formation. Okay.
You get a perfect repeating pattern cube after cube. This is the gamma prime phase. And it's this difference that is crucial when a dislocation tries to glide through the lattice. In the roads, this motion is easy. Each layer of atoms can shear smoothly past the next, leaving the structure looking unchanged behind it. But if you try to do the same thing in the blocks, well, now you're actually changing the order of the atoms.
Which doesn't...
Nickel and aluminum end up sitting in the wrong places.
So it resists that
takes
change.
energy,
Yeah.
so the lattice resists it.
Yeah, okay.
So when a dislocation moving through the roads hits a block, it gets stuck. And that's what makes this alloy so strong.
But if you keep pushing and the stress gets high enough, dislocation can finally force its way in. The catch is that this dislocation leaves the lattice in such a high energy mess that the only way that it can keep moving is if there's a second one right behind it that puts things back in order. So in the gamma prime phase, dislocations have to travel in pairs, called super dislocations.
I need that creation of those super dislocations, and I need that very high stress to be able to shear. So that's why the strength is very high relative to other alloys. What happens is ultimately because you're shearing through that gamma prime with two dislocations, as the temperature continuously increases, you're adding more and more thermal energy in the material. What happens is the atoms are going to vibrate more and more and more. So there's a likelihood, as I'm doing this and I'm oscillating in 3 dimensions, that the thermal energy is going to drive me to actually slip down rather than just slip in one plane. So now if one cross slips, they're no longer on the same plane. think of it as if we're standing in line, and the only way that you can move is if I push you, right? And then I keep on pushing you, and then suddenly you drop. So if I now try to push you, I cannot find you, right? You're not in front of me anymore. Your shoulders are now below me.
Why are you touching?
I should have used the other example, you pushing me, but anyway. But it's exactly that. It's the exact same analogy. There's nothing to push me anymore. There's like, I am not able to do it.
So that is insane for like atomic geometry to just, drop a plane, but that is...
So now you've got these two dislocations that are on different planes, so they can't travel together anymore. And as a result, they're both now locked into place. And you can see that effect on this graph. While steel and titanium strength drops off, in the nickel superalloy, you actually get a peak. That's because the extra thermal energy lets more dislocations cross-slip and get separated. And it's that shuts down the motion of dislocations. But if gamma prime is so strong, why don't we just make the entire turbine blade out of it? Well, that strength comes at a cost. Gamma prime stops the dislocations so effectively that it becomes brittle. All it takes is one crack or a sudden impact and it could lead to a sudden failure. So the real trick is in striking the right balance between enough gamma prime to trap the dislocations and to prevent this creep, but also enough gamma to keep the alloy ductile so that it can bend without breaking.
And in our test, you can see exactly how that plays out.
1,000 degrees and still nothing.
Nothing changes.
Still nothing.
There it is.
There we go.
Oh my gosh.
That's
1100 degrees C.
Is it plastic? Sorry, is it
Stretching.
elastic?
I mean, it's still holding up, like...
It's doing a good job.
That's 1200 degrees C.
Yeah.
1200.
That's a temperature program that stops.
And it's still surviving.
Still going.
But if you push the temperature too far, even this alloy reaches its limits.
Yeah, it does fail.
Cross-slip becomes easier. The paired dislocations can now hop between the planes together. And the ordered cubes of gamma prime start to dissolve, so the dislocations break free and it finally gives out.
It fails.
Oh, it may have just
failed.
Did it break?
Oh yeah, it did. It broke.
Yeah, it fails.
But strength alone isn't what makes these alloys special. When you heat up the alloy, aluminum at the surface reacts with oxygen to form a thin, continuous layer of aluminum oxide.
Right.
Unlike the brittle oxides that form on other materials like steel or titanium, this layer stays intact at high temperatures, protecting the metal below.
And by adding other elements, we can tune these superalloys. Each one brings a specific property that we want. Most modern superalloys contain as many as 10 different elements, all carefully balanced in their relative abundances for the desired properties.
Interesting.
Chromium improves resistance to oxidation and corrosion. Cobalt, titanium, niobium, tantalum, and vanadium help stabilize the gamma prime phase. Molybdenum and iron strengthen the gamma matrix. And then there's rhenium. Rhenium has one of the highest melting points of any metal at 3,180 degrees Celsius. It's second only to tungsten.
Damn!
In the nickel superalloy, it slows the atomic scale rearrangements, enhancing the alloy's resistance to deformation, even at temperatures above 1,000 degrees Celsius.
It tries its best.
It's one of the rarest elements in the Earth's crust, at less than 1 part per billion. And more than 80% of what we mine ends up right here in jet engines.
But to be fair, that is a very good use of a rare material. At least it's dedicating itself to the common cause of transporting people.
Even with these advancements in alloy chemistry, there's still one fundamental problem. And that's that metals are crystalline. Any metal you see, from the tip of this ballpoint pen to the spoon in my coffee cup, they're all actually made up of millions of little crystals stuck together. It's kind of like grains in this sugar cube. If I crush it, it's not like I've broken any individual crystal. I've just broken them apart. It's the boundaries between the grains that are the weak point. And it's the same thing in a metal.
So if we zoom out from the gamma and gamma prime structure, it looks something like this. One crystal is basically a three-dimensional lattice of atoms all lined up in the same orientation.
Right.
But the crystals themselves are all in different orientations. So where they meet, their lattices don't line up. And that mismatch leaves more open spaces and broken bonds.
Right.
And you also get defects there, like vacancies and impurities, all of which make grain boundaries the weakest point. And this also has another consequence. It makes it easier for atoms to move along the boundaries.
And it makes it easy. And they're like very nice failure points as well. Okay.
They become kind of superhighways for atomic diffusion. This becomes even more of a problem at high temperatures when atoms have more energy to move around. Add stress, like the massive centrifugal loads on a turbine blade, and the grains can actually start to slide past each other.
Right, and
the whole structure slowly deforms, stretching almost like warm taffy.
And it's eventually going to find a way to just
as long as it has grains in it, it will creep and fail far more easily. And that's a really hard problem to solve because normally as a molten alloy cools, tiny crystals start to form all throughout the liquid. So you have to find some way to control them.
This is one of our furnaces. They're all induction heated, there's no kind of gas fire or anything like that, and they're all under vacuum, so we only cast under vacuum in the absence of any atmosphere, but particularly oxygen, which is obviously
casting already is complicated as we're casting all those elements in that specific mixture under a vacuum. Wow.
Obviously, metallurgically going to cause us all kinds of problems with oxides.
You start by pouring molten superalloy into a ceramic mold that's mounted vertically and heated to about the same temperature as the melt. The mold fills from the root up toward the tip. At the very bottom of the mold sits a copper plate cooled by water. Its surface is patterned with tiny grooves that act as nucleation points for the first crystals to start to form. It's here that solidification begins. Then the entire mold is slowly lowered out of the hot zone, so the solidification continues in just one direction.
It's a very slow process in the magnitude of hours. Once that's finished, the whole machine will then index round and it will push the completed mold up out of the other side.
Oh.
Yeah, wow. Molten
so
hot
our casting
liquid.
temperatures are roughly 1500 degrees Celsius.
But it's kind of at the same temperature now as it would be inside the jet engine. It's absurd. Like you're making the turbine blades at the same temperature that they're going to operate, but like here they're liquid.
Yeah.
Now, if we just did that on its own, you'd end up with a blade that looks like this.
Here's a directionally solidified blade. And what you can probably see there is the contrast between the grains. These are all different crystals, but they're all running on this axis of the blade, which makes it significantly stronger than an alloy that is cast, where all of the crystals are separate from each other.
So those are like individual crystals?
These are individual crystals, yeah, absolutely. So we're looking at crystals on kind of a macro level, where normally we'd be talking about crystals on a micro level.
That's fascinating, isn't it?
In a rotating turbine, the blade is being pulled along its length, with columnar crystals all lined up along this span. The blade can carry those stresses far more effectively. There are no grain boundaries that cut across the blade, creating weak points for it to crack.
But scientists have found a way to do even better. If you introduce a bend in the mold just above the chill plate, something strange happens. The number of columnar crystals that make it through drops sharply. And if you add another bend, even fewer survive.
So,
I'm sorry. Hold on. You're telling me all of them are individual crystals of metal? There's like, we get a spoon or like a fork, you have like different crystals of metal in them. You're telling me they're pouring molten hot metal that's going to flow from beneath, go up a couple of turns, and it picks up one crystal that forms the bro, okay, now that is...
Engineers added a helical passage known as the pigtail here at the bottom.
Sure, they can see where that got that name from.
Bottom of the mold.
The pigtail is doing the job to select the single crystal. The spiral is going to choke out every other grain bar one. So we're only going to have one grain that is then...
Bro, that is actually... Who thought about this?
Then going to grow through the entirety of that blade and cast that blade as a single crystal, or at least...
That is... Bro, the work that has to go in and getting that done right is insane. You have to repeat this process, and if it's one crystal, you get the extra benefits. But I'm guessing the amount of chances of impurities or anything else or any other crystals forming, so just forming out of one crystal though, damn.
That's the theory.
That's crazy.
Well, clearly, that's crazy is actually valid here. That's insane.
So this is a starter attached to a spiral that we've etched so that we can reveal that structure. So you can see down at the bottom, we are starting to grow directionally solidified grains. But as we get up here, we can start to see that we're growing directionally solidified grains. And then as we're going up the spiral, the grains are starting to be choked out by the upper surfaces of that spiral until when we get to the top, we're just as a single crystal, and then that allows
a
that
single
to grow
crystal
right
to
the way
grow
through the blade.
Yeah, that's amazing.
And what we should end up with is a blade like this. So this is a blade of a single crystal.
And you don't see any shading, no macroscopic crystals, nothing. This is a single, wow.
It's a really impressive thing to look at.
I would imagine so, because this is human ingenuity at its finest. Damn.
The shimmer is beautiful.
This is what keeps pressurized metallic cans in the sky. Yes, I can see why. Yeah.
Even after the blade solidifies, it's still not ready for the engine. It's...
Brother, what? I mean, fair enough. We just saw that it melted at 1,200 degrees. I'm guessing there's some treatment again.
Heated again, almost to its melting point. And that might sound risky because we've spent all this time making sure it's a perfect single crystal. But this heating step lets the atoms shuffle around just enough to spread out evenly.
So even you de-stress the metal. Okay.
Form the final desired microstructure of the gamma and gamma prime phases that make these superalloys so strong.
And as if casting as a single crystal is not enough, actually the orientation of that crystal is also of paramount significance. So you may have cast this as a single crystal, but if the crystal orientation is off by a certain amount, you get completely different stress responses within that blade.
Today,
brother, that sentence is mad. That's like saying if that crystal formation that starts at the base of that pigtail is not angled within specification, you're going to have very different stress strain responses. Of how the hell do you even test for it? Like, I'm guessing there must be a way to understand. I'm guessing obviously that's going to be proprietary, but imagine there must be ways to identify like the stresses and the general direction of those. There must be a way to like have quality checks on those blades. Otherwise you'd have blades failing randomly.
After decades of development, over 95% of blades can be cast successfully as single crystals.
95% as a number is insane. That's like what? Out of 100 blades created, 95 passed the test. Wow.
Just think about how incredible that is.
Yeah.
We've gone from a turbine blade that contained on the order of 50,000 crystal grains down to just one.
Mm-hmm.
When we grow these things, they don't solidify as a uniform front. On a microscopic scale, the solidification front looks like a forest of tiny tree-like branches called dendrites that are pushing their way into the liquid.
Mm-hmm.
At first glance, it looks messy, like millions of separate trees jostling for space. There are up to 10 elements in there, each with its own density and melting point, yet somehow every one of those trees is locked into the exact same crystal lattice. So the final crystal is comprised of more than 6 times 10 to the 24 atoms. That is more stars than there are in the observable universe.
Oof.
And all these atoms are repeating the same pattern, perfectly aligned from root to tip. This completely transformed what jet engines can do.
Right.
Single crystal blades can withstand stresses and temperatures that would destroy ordinary alloys.
Yeah.
They last up to 9 times longer against creep and thermal fatigue, and are more than 3 times more resistant to corrosion than blades made from multiple grains. That's why modern jet engines can now run for 25,000 hours between major overhauls.
Which is insane to even think about. Wow.
Something that would have been unthinkable before single crystal blades. And the impact has been huge. Between 1960 and 2010, jet aircraft became about 55% more fuel efficient. And a huge part of that improvement comes down to advances in these nickel
in material
superalloys.
sciences, yeah, especially.
Back in the 1960s, flying was a luxury few could afford. A one-way flight from New York to Paris would set you back $310, which is about $3,750 adjusted for inflation. But as engines became more efficient, able to handle hotter cores, and equipped with much larger fans, airlines could carry more people farther using less fuel. So tickets got cheaper, and air travel exploded.
Yep.
Today, at any given moment, there are roughly 10,000 to 14,000 planes in the sky. That scale of movement is possible because of these turbine blades.
Yeah. And if they started to fail, we would know. People would know.
In the furnace, the nickel superalloy outperforms all the other samples, surviving up to 1,200 degrees Celsius. But wait, that's still 300 degrees less than the temperature inside a jet engine.
I was going to say, you saw them fail at 1,200. How the hell are they standing 1,500 degrees inside a jet engine? How?
So why don't the blades melt? Well, there are 2 final layers of defense. The first is built into the shape of the blade itself.
We then have to leach the core out. So we do that in a caustic solution of potassium sodium hydroxide under pressure and temperature to leach the core out. That will leave those core passages completely empty.
And those passages are the real secret to the turbine blade's survival.
Oh, that's interesting. So like the original core piece that you do leave. Oh, okay, that's interesting.
As the air is flowing through, it is turbulent, and as such it can remove much more heat from the surface of the blade than
Is it these ridges here that we're talking about?
Yeah, these ridges here.
They're
disturbs the airflow.
to trip the flow
to trip and turbulate that airflow so that it's removing as much heat as possible from the metal. So then we get onto the really juicy part, which is film cooling. So we talked about the ice cube in the oven stat keeping our blades as cool as possible. So this is where we start to drill in what we call film cool holes. And what we're aiming to do is we're aiming to get into those cooling passages. So we saw that core earlier on.
Right.
They are the cooling passages inside. And these holes have got to get right into those cooling passages to allow that air to come out. And the air is then going to blow as a film over the surface of the blade, a film cool hole to create a film of air, which is preventing that metal from melting in those temperatures.
This cooling air isn't exactly cold. It actually comes from the high pressure compressor section of the engine at around 600 degrees Celsius.
Right.
But that is cool enough to help keep the blades from melting.
From reaching
But
the...
it's still not quite enough. And you can't just add more cooling air because...
I imagine because if it's a bypass engine and you're putting a good 80% of your air through the bypass, you don't want to divert more of that bypass back into the engine, which reduces your thrust and efficiency, right? It's counterintuitive, right? So no.
Because every extra bit of air you use from the compressor, you lose from thrust and actually make the engine less efficient. So every turbine blade is also coated with two protective layers. First, a thin metallic bond coat that resists oxidation. And then a ceramic top coat. Even though it's only about 1/4 millimeter thick, this ceramic coating can keep the metal beneath it 100 to 170 degrees cooler than it would otherwise be.
And I'm guessing that combined with the fact that it has the air holes are just enough to make sure they don't melt.
And this is the final barrier that stops the blades from melting.
Okay.
So now we've got this insane piece of engineering that can survive the 1500 degree gas, the intense load, and the oxidation. Problem should be solved. Well, it would be, except for one thing.
At 36,000 feet, you wouldn't believe this, but there's dirt and dust in the atmosphere that our engines are ingesting. The dirt and dust comes and it sticks on the blades, but it also goes through the whole cooling circuit.
And plugs in those holes.
Blocks the cooling from getting through to cool the blades.
I imagine that would just overheat these blades over time and just cause them to fail,
And then
but then I imagine like if it was a major problem, it should have showed up as like major weaknesses. I mean, there have been accidents in the past caused... I mean, there have been accidents in the past that have been caused by, these fan blades separating, but they've been much like rarer in between. I don't think it's like a very common thing that happens, especially with jet air blades. But the thing is, with the amount of planes taking off, if that was such a serious issue, shouldn't have it started causing problems these days?
The blades burn up. Usually every time I get on a plane, I'm thinking this is never going to work.
I mean, it does feel unnatural, doesn't it? When you sit on a plane and you hear the engines roaring, and yes, it's powerful, sure. But then feeling it take off into the sky, you're like, bro, this is insane. And it's not being uncomfortable. It's just something, naturally in the back of your brain telling you, there is no way this multi-1,000+ ton beast of hunk and metal and fucking, fuel, aluminum pressurized can is going to take jump into the sky and have air supporting it while you goes, and it's insane seeing it happen time and time and time again. It's crazy.
Oh, I mean,
it really is
incredible how an engine can work because there's so many.
Bro, I get it. Like this is a metaphor for resisting gravity. And at this point, if you're a plane in the sky, gravity is not necessarily your best friend.
Many moving pieces. There's so many parts. The environment's so terrible. And now we have this dust and dirt, which is really bad.
Yeah, for the engines.
I am at testbed 80, and they're about to fire up this jet engine and then throw dust into it.
The same stuff that makes up sand and volcanic ash.
And this is the thing. There have been accidents based on just volcanic ash alone, and that to a British Airways flight.
Exactly what real engines encounter in flight.
So this engine is the 97K. It goes on the A350 and is our higher thrust version of that, so 97,000.
That must be like a A350s, meaning like it's the current I think it's current state of the art long range engines. Like I'm guessing from Airbus, because I think the A350, they're different variants, but I think they're some of the longest range variants of the Airbus lineup today.
Pounds of thrust is what this engine's producing. When we're running an engine like this, we try and carefully recreate exactly what happens in service.
How much dust goes in the engine?
Not very much. It was surprising when I found out exactly how much we put in.
Yeah, I was going to say that doesn't seem like a lot. I imagine because you have to understand there have been enough accidents in the past. Like hell, the Hudson River landing was caused by a flock of birds hitting both engines and then shutting them down. Which I know, in first glance, you're like, oh my god, so much metal. How could birds shut down engines? But it's like, hey, damaging those fan blades and internal delicate components can shut down planes quickly. But yeah, I don't think that's enough dust. I'm gonna be honest. I'm most likely a high silica, like sand-based dust from volcanic eruptions melts and sticks to those fan blades, like really heating them up. So it's not even a fact that you can get the engine started. You have to get the engine started without it catching on fire, which is
in the order of tablespoons worth per.
I mean, come on, really? That's not okay. I guess they must have their own scientific reasons for testing, but that just seems a little bit of a, come on, you got to know how far you can push the engine. So come on.
Per cycle.
I mean, it is also multi-million dollars. I mean, I imagine it makes sense. They don't want to just, test for the sake of testing. It'd be like, well, we don't need to know the limits of the engine. Fair enough. Okay.
Master on. Ignition power on.
It's still terrifying being close to it, isn't it?
Master fuel lever on. Start request in 3, 2, 1, now.
So what does the dust actually do inside a jet engine?
So once it gets through to the hot section of the engine and hits kind of turbine blades, it's going to be melted. And so it sticks to the outside of our turbine components, and it slowly rips layers of that
protective
thermal barrier coating off. And then you lose your temperature reduction that comes from the barrier coating, so your nickel alloy underneath it gets hotter and hotter, and that's when it stops.
Okay, it could be possible that they might not be thinking of this like a one-time event. I think it's just the kind of dust you expect to build up over maybe 10, 20 years. And hopefully by that point in time, this is like trying to simulate what those reductions in those coatings over that supposed timeline is going to affect the longevity of the engines, right? Which I think is fair.
Deteriorate the turbine.
Just cool. Yeah, it deteriorates. That's fast. That's still insane.
That's why engineers at Rolls-Royce are still refining these blades, developing new ceramic coatings designed to resist molten dust and extend the life of the turbine by up to 30%.
That's crazy.
That's just the latest step in a story that's been unfolding for decades. These blades have been refined and perfected to the point where they operate right at the edge of what is physically possible. You're always on a knife edge, pushing every material, every process to the limit to build an engine that can do the seemingly impossible.
It is, isn't
run
it?
hotter than its own melting point.
Right.
The more I learned about the brutal environment these blades have
That's such a hard line. Running hotter than its own melting point. Wow.
Survive, the more it felt like they shouldn't work at all.
Yeah.
And yet
they do.
Every day.
Jinx.
These machines carry millions of people across the world, and we barely stop to think about them. They're a monument to human ingenuity, what happens when we refuse to accept limits, when we turn the impossible into the routine.
Turning the impossible into the routine. That's a solid way to end the video. I think airplanes have always fascinated me just as much as space flight. I mean, the first time we saw space boosters landing by themselves, is just monumental. I feel like that's just the start of the next frontier of human exploration. But also seeing that, hey, planes take off and land daily is just, you never stop and think about it until you see accidents, or you see, of course, there have been recently many accidents, especially 2024, 2025-ish, especially 2025. This year, there's been a lot more I wouldn't necessarily say that accidents are caused necessarily by engines, but as much as it's been by either improper maintenance or just poor planning or human error. But regardless, you want the machines that carry people every day to be as safe as possible. And I think this just shows the amount of effort that goes into building those things, the power plants. And I think it goes to show just, how critical it is in, pushing the frontier of human exploration, bro. Because if people didn't really think it's possible and didn't really take the chance of building technology like this, we wouldn't be flying anywhere. So it's just insane to see this. Human ingenuity at its finest. But that's about it. I feel like I am yapping. Hope you guys enjoyed the video. Like, comment, subscribe. And I will catch you before we pass to the next one. Peace, take care. Nice.